Hello class, this is Adam Ward, and I wanted to work through one more example using the energy equation with you today. And so in this example we're given an aerator that would be typical to find in something like a wastewater treatment plant. Flow rate of 3 cubic feet per second, 4 feet of head loss between points 1 and 2, and given a velocity at point 3 where the fluid actually exits the aerator as a free jet. Two parts here. First, find the power added to the system by the pump. And so to do this, we're going to apply the energy equation from point 1 to point 2, thinking about the streamline that I've drawn in black. So we'll go ahead and write out our equation. On the left-hand side is the energy where we end up, point 2. That's equal to where we started, the energy at point 1. So that's all the Bernoulli equation in those first 6 terms. Plus any energy added by a pump, minus any removed by a turbine, minus any due to head losses. And so for this problem, both the pressures at points 1 and 2 are equal to 0. We're working in gauge pressure. And at point 1, velocity is 0. That's typical assumption for us. At point 2, recognize this is the location where water stops moving vertically upward and begins to move downward, and so the actual velocity at that point is 0, so we can zero out that term as well. No turbine, so I've zeroed that out, and so you're left with the elevation at point 2 is equal to the elevation at 1 plus the head due to the pump minus the head losses between 1 and 2, which we were given. And so we can go ahead and plug in values and we can solve for a pump head providing 12 feet. Recognize we were not asked for pump head but for pump power in this problem, so we'll use our power equation. Power is equal to the specific weight of the fluid times the discharge times that pump head. So plugging in constants for water and the flow rate and geometry of the problem, I calculate 2,246 foot-pounds per second. And into more meaningful units, we might recognize that 1 horsepower is 550 foot-pounds per second, so I would calculate 4.08 horsepower added by the pump. Part B of the problem asks us to determine head loss from point 2 to point 3, and so again we're going to apply our energy equation, this time along the flow path that I've now drawn in black, connecting point 2 to point 3. So once again, start with that generic energy equation. Where we end up equals where we began plus and minus the changes that occur along the way. We can zero out pressure at both locations. We'll zero out the velocity at point 2 as we did previously, and we'll zero out those pump and turbine terms because neither exists in this problem. And so you're left with the equation I've written here. Plugging in values for all of these variables. It's fairly straightforward to solve for a head loss of 9.94 feet between point 2 and point 3 in this problem. Now if you've gotten through this and you're still wanting to work more on the energy equation, I've thought about a few extensions to this problem for you. One of those relating to pump efficiency. So if the efficiency of the pump was 0.6, what power of the pump would actually be required? So how much energy would we have to put into the pump, or what size pump would be required to actually deliver that 4.08 horsepower to the fluid. As another extension, if you were given a pump power, with or without efficiency, your choice, what would the flow rate be through the system? So for example, if given a pump of 10 horsepower, what discharge would you expect moving through this system, assuming that the geometry and the head loss between points 1 and 2 remains unchanged? Finally, as another way to practice, you could repeat problem number 2, but assuming that in this case the head loss is not simply 4 feet between points 1 and 2, but the head loss is actually a function of velocity itself. When we get to minor losses in this class, you'll see that this is actually a better representation of head loss in the system, and so this would be a chance for you to practice the energy equation and get a sneak preview of what minor losses will look like in our systems. I hope this example helps you all to understand the energy equation.